And our next speaker is Graeme Best. He's going to talk about decentralized Monte Carlo tree search for active perception.
Okay, thank you, Nancy, and thanks, Dylan, for keeping everyone awake in the last session. So what I'm presenting here is a new type of Monte Carlo tree search, a decentralised form of this, that solves this very general multi-robot problem. So my name's Graeme, and this was done with a team at the University of Sydney, Tulane University, and University of Technology, Sydney. So what we often do as roboticists is that we task our robots to perform perception tasks. So we've got three examples here where we've got a robot moving through a farm closest to me, underwater in the middle, and on the far side through some forest. And as the robot moves through these environments, it's using its onboard sensors and perception algorithms to understand some property of these environments. So for example, what we see here is the fruit in the trees, the health of the coral reef, or the location of wildlife. Now what usually happens in these tasks is that the robot follows some predetermined path, such as what you see in the picture here. And we believe this is holding back the full capabilities of autonomous robots. So instead what we think they should be doing is this idea called active perception. And this is where the robots plan their viewpoints and plan paths of these viewpoints based on the current knowledge that they have and the objectives of the mission. And the main idea behind this is that if you do this, you'll collect better data. If you collect better data, this is going to improve the performance of your perception algorithms. Now, this idea of active perception has been around for years, even decades, but it hasn't really taken off as much as we think it should have. And one of the reasons behind that is the algorithms just don't meet the needs of these applications. So if we look at this example system here, this was used for active object classification, shown in the picture. And this system diagram on the right-hand side, you can see that there's various components of the system that need to work together. So at the top, we have this planning component. That's where the robot needs to plan what it's going to do next. It needs to navigate and execute part of this plan. And as it's executing part of this plan, it makes observations along the way. And these observations should be processed and fed back into the belief of the world. Now, when we're talking about active perception, this belief of the world now needs to go back into the planner, and the planner should update based on this new information. And so a key challenge for this type of system, and what we're interested in this work, is this idea, is this planning component. And in particular, we want to do efficient online planning with these four properties. We want to have multiple robots that work together, preferably in a decentralised way. We want to have long planning horizons rather than greedy planners. We want it to scale up to large environments rather than just small, very constrained environments. And of course, we want to do this all online on board a real robot. So when I talk about decentralised multi-robot planning, so there's three main components that we believe are necessary for it to be fully decentralised. And so first, each robot should be interested in planning its own paths, more so than everyone else's. Also, there's some kind of communication available, so we can use this communication medium to coordinate the plans between agents. But we don't want to rely on this too heavily. This communication may drop out when the system needs to be robust to that. And so just briefly on related work in this planning problem. So often first step is to do some kind of greedy planner, but this can be shown to be arbitrarily poor unless you have certain assumptions such as submodularity. So instead we want to scale up to plan over sequences of actions or non-myopic cases. And so some example solutions are to solve some very problem-specific solutions such as a TSP type problem on the right, or you have very general solutions such as POMDP solvers that fit into this. And so one closely related idea is this decentralised POMDP. And so the problem that we're presenting here is quite similar, but usually in this related work, the focus is on offline planning and then online execution by looking up to a lookup table. So instead, we're trying to bring this planning component online on board the robot. Okay, so I define our problem here, and it's this very general problem that we're trying to just find the paths of the team of the robots, that's X1 through to XR, that maximises some objective function for the team of robots, which I'm going to call G. So we make no further assumptions in that, except that we know what G is. And so the planning scenario that we're interested in is this decentralised planning. So robot I is going to plan its own sequence of action while considering these three components. So the belief of what it thinks the other robots are going to do, the global objective function G, which it knows, and some action costs or budget. Okay, so now we're going to try and solve this problem. So what I'm presenting here is a new algorithm which we call Det MCTS, Decentralized Monte Carlo Tree Search. And there's three main components here. So this is what's happening on board one robot. And so to begin with, it's going to grow a search tree shown up the top there. And it's a search tree over the actions for that single robot. And then on the right-hand side, we're going to compress this search tree using a distributed optimization process into a probability distribution over paths. And then on the left-hand side here, we're going to communicate these probability distributions between the robots. Now what happens after that is that this communication then feeds back into the tree, and we can adapt our tree search based on this new information from the other robots. So for the tree search component, what we're going to use is this Monte Carlo tree search. And so just briefly, Monte Carlo tree search is this biased random sampling of a tree. It has this nice properties of being any time, and only requires evaluation of full paths, so there's no intermediate heuristic functions required. And so the algorithm summarised briefly down the bottom here is that we select some part of the tree to expand, we then perform a simulation from that point in the tree, and we collect statistics, particularly the reward function, and feed that back up the tree, back up to the root node. And this process continues until your computation budget is exhausted. And the main power of this Monte Carlo tree search is when we start using this upper confidence bounds as a way for expanding out the tree. So this equation you see in the middle here, if you expand based on this equation, is it balances between exploitation, so what we believe is promising, and exploration in terms of what we haven't seen yet. And so then you get this picture down the bottom here where you bias your search towards different areas of the tree, and you grow at different rates at different parts of the tree. So this works well for the single agent case, but there's a few extensions that we need to do for this multi-robot problem. So firstly, we need to consider that the objective is a function of all robots, not just a single robot, but the tree is only for a single robot. So what we're going to do is going to estimate the expected global reward by first doing the standard rollout policy for myself. And then for the other robots, I'm going to sample this probability distribution on the right, which I'll come back to a bit later. And then together we evaluate the utility function for this joint sample. Now, the other problem that we have here is these distributions, which once again I'll come back to. It's changing over time. That means our reward and function is changing over time. And so that kind of breaks the Monte Carlo tree search in some sense. But there's one way that we can get around this. And what we do know is that the most recent rollouts are more important and more relevant to the search. And so what we do here is we're proposing this discounted empirical average instead of a standard empirical average, which is biases towards more recent rollouts and makes them more important and contribute more to the average. And so the main reason that we do this is by introducing these functions here, is that it brings back that exploration-exploitation trade-off now comes back into it. So now getting to the next part of the algorithm, this is the probability distributions I've been mentioning. And so what we're going to do is compress the tree. So the main idea of this is if we compress the tree, then we can communicate them between the agents, and also we can plan based on this distribution. And so what we're going to define here is the x-axis, the domain of this distribution, is selected as a subset of paths with the highest expected reward, so far indicated by the search. And our y-axis, the probabilities, are going to be defined by this distributed optimization, which I'll come to now. So we're going to do distributed optimization over this probability distribution. So in the general case, on the left here is that this probability distribution can be a function of all paths, all robots, but that's very hard to decentralize to distributed optimization. So instead we make this approximation on the right-hand side where we now have a product distribution for each robot, and now we can optimize in a decentralized way. And so to achieve this, we adapt this type of variational method called probability collectives, and has other names with similar variants. And just quickly, it's basically doing a distributed gradient descent over the space of probability distributions, where we sample the rewards, and then we have this descent scheme that balances between improving the rewards for the system, as well as balancing with the entropy so that we don't go too fast towards a single solution. And so just to come back to this picture now, so we've shown the tree and the probability distribution. Now we can communicate these distributions between the agents. Now the idea is that once you communicate the distributions, that gets fed back into the tree, and the tree now updates based on this new distributions. So this is all happening on each robot, and it's all decentralized. Okay, so what I've presented here is a decentralized planner for quite a general problem. So for such a general problem like this, it's usually quite difficult to make any strong guarantees of, say, global optimality. And so we can't really do that here as well, but we can, unfortunately, make some guarantees or give some analysis of the convergence. So we have two main results here. The first is that we can show that the DUCT, the discounted policy, when we're changing the distributions abruptly, what happens here is that we can still maintain that we're balancing between exploration and exploitation. The second main result here is that the way that we're restricting the domain, we can show that this is a type of doing important sampling. And we can give some guarantees that come back to the probability collectives idea, where we're converging to a distribution that minimises a Kao divergence between the product distribution and the joint distributions that we saw before. So I'm a bit out of time, but I'll go through this quickly. So I have two sets of experiments. So the first is that we have this generalisation of the orienteering problem where we need to visit these disks here and they're following Dubin's paths. And the idea here is that they just need to visit as many disks as possible. And so in these results, what we showed is that decentralised Monte Carlo tree search outperforms a centralised version. And we also made a comparison for communication. We'll show that even if communication drops out, it still performs reasonably well. So the second set of experiments looked at this active object recognition task. So this is where we use a real perception model and a data set that was recorded by this robot to look at different different objects in the environment. And what we showed in this case particularly is that the greedy version of our planner did quite poorly, and it concentrates at things just around the start location, whereas the planner over sequences allows us to explore the full space. So in conclusion, what we propose here is a centralised algorithm for a general problem. Won't go through this, but in particular we're interested in how can we generalise this to other problems, and I'll be interested to hear from you guys what other problems that this planner could relate to. So dirty laundry. The main thing that's come up is that we can't consider hard constraints between the robots. I think that's something that we have ideas for, but it's not directly considered. We assume a fully observable state. All agents know and agree on the objective function. And as I discussed before, analysis does not guarantee any global optimality, but we do show some parts of it. So I think that's time up, but just quickly, main thing that we want to do next is to bring it into other perception models. One particular application is this idea of picking apples in a tree. We first need to observe the apples and combine it with manipulation tasks. All right, thank you. Do you have any questions?
Thank you. Questions? Back there?
I find the work very interesting. I'm curious, so I can think off the top of my head like 3 different mechanisms why this framework would improve over just a centralized framework. And I'm curious if you have any insight into like which one of those are the most important. And the first one is just you've given, right, if you have an N robot team, you've given N times more computational power to the problem. The other one is your tree is now maybe, in the paper at least, you go into more detail, but it's 1/n kind of the depth. And then the third one is maybe there's some branch and bound sort of stuff that's going on here where the focusing that you're talking about, right, the important sampling, like that is kind of orthogonal to the previous 2 ways. And all of them may help, but do you know which is kind of the main helper here?
Yeah, so I think that all help, but particularly the second one. So compared to a centralised tree where you're branching over the joint action space, and suddenly your tree explodes very quickly. Whereas when you split up into single trees and suddenly got smaller trees and you can explore deeper depths of that tree much quicker. And I think that's where the main benefit comes in. But as you say, I think they all contributed a little bit.
Yeah, thank you. I just a follow-on comment. I would say in extensions to the work, you could consider different ways of giving N times computational power to the single robot just to like remove that as a thing, or having all the robots kind of independently plan and do an OR parallelization where you then have them vote and you just use the best one found like by anyone independently, and that way you throw out like that other thing is what's going on.
Yes, so in terms of your first comment about really we've got 8 times computational power, we've got 8 times more robots. But the improvement was more than 8 times. So I didn't really talk about that, but I think it's more than just that.
Oh yeah, very interesting. Thank you.
Thank you.
Another question? Okay, well, let's go ahead and thank him
Thank you.
again.